Let's take a closer look at sequences now. We kind of did an overview of sequences, and some of the stuff that I'm about to do we've touched on, but I want to go ahead and just make it a little bit more formal now. And let's start off with the idea of the limit of a sequence. So let's let f be a function of real variable such that the limit as x goes to infinity of f of x equals L. Now, before I did a couple examples where I had an, and I just took the limit as n goes to infinity, and I said, yeah, you know, it's okay, you can do this, don't worry about it. Well, this is really why you could do this. What we're going to do is take an, if an is a sequence, and what we're going to do is match up an with fn. So fn will equal an for every n in the domain of an, basically. So for every positive integer, this is true. Then the limit as n goes to infinity of an is also equal to L. So technically what we should be doing is taking this limit after we've matched f of x up with an, taking this limit, and because this limit equals L, that implies that this limit over here will equal L. Now, essentially what we're doing is, let's just suppose that an looks like this. So you have 1, 2, 3, 4, 5. Okay, let's just say that an looks something like this. And asymptotically, this is going to converge to some value, which I'm going to call L. So this is the line y equals L. What we're actually doing is saying, hey, look, the idea of a limit we really want a continuous function on. So I'm going to take f of x, and I don't care what f of x does over here. The point is, when I hit here, f of x will overlap an at every point. So if f of x asymptotically, or in the limit goes to L, then an must also go to L because f of x and an match up at every place where an is defined. So essentially that's what this theorem is doing, and that's why earlier I said, well, you know, I'm just going to take the limit as n goes to infinity of an. Because I knew that this thing here actually exists. So let's take a look at an example. Let's find the limit as n goes to infinity of 1 plus 1 over n raised to the n. Now, the way I'm going to do this is I'm going to note that f of x, I'm going to let f of x equal 1 plus 1 over x raised to the x. And over the domain of an, where obviously this is an, n equals 1, 2, 3, so forth, etc., this is defined. See, for n equals 0, this would be x would be 0, 1 over 0 would be undefined, but we will start n off at 1. So this is defined. This matches up with an of 1 plus 1 over n to the n for n equal to 1, 2, 3, and so forth. So really all I need to do is find the limit as x goes to infinity here, and that will give me this limit. So I want to look at the limit as x goes to infinity of 1 plus 1 over x to the x. Now in the limit, if we just do a substitution here, this piece would go to 0, and I would end up with something that looks like 1 to the infinity, which is an indeterminate form. So we need to do something about this. We need to work with this. So what I'm going to do is say, okay, y equals the limit as x goes to infinity of 1 plus 1 over x to the x. That implies I really want to get this thing out of there. I want to get this thing down. So I'm going to take the log of both sides. So ln y equals the limit as x goes to infinity of x ln 1 plus 1 over x. And now I want to take a look at this thing and say, okay, what happens if I rewrite this? And I'm going to write it in terms of, whoops, not a limit yet, I'm sorry. Ln, natural log of y, equals the limit as x goes to infinity of the natural log of 1 plus 1 over x over 1 over x. See, this 1 over x is this x right here. Because if I, the a over b over c over d equals a over b times d over c. So I just went the other way and I just brought 1 over x down. These two are equivalent. Well, see, now what happens is if I take this limit as x goes to infinity, this becomes ln 1, which is 0. This becomes 0 over 0. It's another indeterminate form. So what I'm going to do is I'm going to apply L'Hopital's rule to this right-hand side. So ln y equals a limit as x goes to infinity. If I take the derivative of the numerator, I get 1 over 1 plus 1 over x times the derivative of the inside, which is this negative 1 over x squared. That's the numerator. The denominator is going to be a negative 1 over x squared. So these will obviously cancel. So ln y is equal to the limit as x goes to infinity of 1 over 1 plus 1 over x. Now we're okay. We can go ahead and let x go to infinity, because as we do, this will go to 0, and what I get is ln y is equal to 1. Well, that would imply that e to the ln y equals e to the first. Well, e to ln y is just y. That implies y equals e. But remember, y was our original limit. Therefore, the limit as x goes to infinity of 1 plus 1 over x to the x equals e, which implies then that the limit as n goes to infinity of 1 plus 1 over n to the n is equal to e. So this limit simply equals the Euler number, e.